Hello everyone, welcome back. So in this video we're going to talk about how to draw complex Lewis structures and determining the geometries, and that includes both electron domain and molecular geometries. So in previous lectures and videos we talked about how to draw Lewis structures, and we're talking about very simple and basic Lewis structures, and then we looked into vector theory. So really what this video wants to do, and what my goal for you is to really understand how to go about looking at specific molecules and trying to understand a deeper into what each of the structures might possess. Now, why is this important? Because not everything is going to be based around an individual carbon atom. Molecules can be very large, and when we deal with these larger compounds, the question is how you go about determining their geometries, how do you determine their hybridizations, etc. And so that's the goal for this, is to try to give you a little bit more firmer understanding on what to do and when. So I'm going to start this off with just a very simple molecule, and that is CH4. Now CH4, based around the carbon. The carbon has 4 valence electrons. Each hydrogen has 1 times 4. It gives you a total of 8. Now, nothing new here. You've got the carbon, and you're going to have 4 hydrogens that are single bonded to the carbon itself. So the hydrogens are single bonded to the carbon. Now, in this particular case, you have 4 electron domains, and so that puts you in a tetrahedral arrangement for the geometry. So yeah, this one's easy because it's just one individual carbon. Now, what we're going to do is we're going to branch out. So what we're going to do now is we're going to look at a compound that's called ethane, which is C2H6. Now, ethane has 2 carbons, and so you go about figuring out the number of valence electrons. And you have to understand that the carbons are all going to have an octet. So now we know that there's going to be a single bond between the 2 carbons here. We're going to split the difference with the hydrogens. And so you're going to have 3 hydrogens on the surrounding carbon atoms. Now this molecule, a little bit more complex than the first one, because now if I ask you to figure out the geometry or even the hybridization, you got to be careful, and this is the biggest mistake students make, is that they want to look at every single bond and then count those as to the overall hybridization or molecular geometry. Well, you can't do that, all right, because for one, if you were to count all these, you'd have 7 bonds. Well, there's no 7 domains to begin with. You have 2, 3, 4, 5, and 6 domains. So that doesn't even make sense. So what we have to do is we have to break it down into the individual carbon atoms that are going to be found as centers. Now you say, well, what do you mean by centers? There's more centers. Over in the first molecule, we looked at the fact that you have 1 carbon atom. Well, that's easy. Now in this molecule, you're going to have 2 carbons. Well, each carbon itself acts as a center, and so that's where we're going to figure out our domains. So now the nice thing about this is if you draw a line down the middle, both halves are the same. So once you figure out one, the other is the same. There's no difference there. So we're just going to focus on 1 carbon atom. So we're going to look at the left carbon, and you can see that there are 4 bonds around there. So you have 4 electron domains, and this shows up as being tetrahedral as well. All right, so now that one's not too bad because both carbons are essentially the same geometries. Now if we were to talk about hybridization, they would both be sp3 hybridized because both have the same number of electron domains. Now, let's say that we have another molecule where we have a CH3 group and a COH group. All right. So Now this molecule, you're going to have, again, the 2 carbons in the middle. You're going to have the 3 hydrogens on the left carbon, and you can see how the formula is written out there. You can see you would have this configuration. Now, the second carbon is going to have an oxygen and then the hydrogen attached to it. So the hydrogen obviously is single bonded to the carbon, and that leaves you with 2 valence electrons on the carbon that are free, and so that's going to be bonded to the oxygen and making a double bond. So now, so as we see in this molecule, we have 2 carbon centers. You have the left carbon and the right carbon. Now, the left carbon itself is similar to what we saw already in the previous 2, where it has 4 electron domains, and it has a tetrahedral arrangement, and it's also sp3 hybridized. Now, the second carbon that you see on here is different. So now this carbon here, you have the 1, 2, 3 electron domains, and so that would suggest that this one is going to be trigonal planar with its molecular geometry, but the hybridization is sp2, and that's because of the fact of the way the bonding is oriented around the carbon. So this is an example that shows you that you can't always assume that the geometries and the domains are all going to be the same. In this particular case, they are not the same. So let's look at another example. So now let's look at ethanol. All right, so ethanol, so CH3, CH2, OH. And so you have the carbons that are going to be single bonded together, just like we saw before. You have the hydrogens around the first carbon. Now the second carbon, you have a CH2OH group, so you're going to have 2 hydrogens that are attached to the carbon. That is indicative right here because of the way it's written out in this formula. But then you also have the OH group that's bonded to the carbon, so you're going to have the oxygen. And keep in mind that you still have to follow the activity rule. Don't forget to count the valence electrons. So the carbon has 4 around it, and then each carbon's 4, and then the oxygen has a total of 6 that you see here. So now the first carbon, the second carbon, they are the same as far as the number of domains in the molecular geometry and the hybridization. So there are 4 electron domains. We've seen this. This is tetrahedral, and then it's sp3. It's the oxygen that we're going to focus on here. The oxygen itself has 2 bonding pairs and then 2 anti-bonding pairs. So 2 plus 2 gives me a total of 4 electron domains. Now this one is not tetrahedral because it has those 2 lone pairs. This molecule, this particular center, represents a bent molecular geometry. Now, since it still has 4 electron domains, its hybridization is still sp3, so that doesn't change necessarily. But the geometry itself does change because of the way that it has 2 lone pairs and the 2 bonds. Now, so as we get a little deeper into this subject, we can look at a bigger molecule. And so let's say we look at I'm going to say cyclobutane. Now, cyclo just means that it's a cycle, it's a ring, and butane itself has 4 carbons. So you're going to naturally have 4 carbons bonded together in a single bond. So the other thing we're going to look at is that each carbon still has to have the octet, so you still have 2 lone pairs on each of the carbons. So in cyclobutane, it has, we were talking about the lone pairs here. So it's going to have 2 hydrogens to each carbon here. So you have a hydrogen here, single bonded. You have another hydrogen here, and hydrogen, hydrogen, and so on and so forth all the way around. Now, we're just going to look at one carbon here because it's symmetrical all the way around. So we're just going to focus on this carbon here. You could look at all the carbons, but it's not necessary because they're all the same. So this carbon has 4 electron domains, and therefore it is a tetrahedral arrangement along with sp3 hybridization. All right, not too bad, but the thing is that you know the question that you might ask is, how would you go about figuring out that it is a ring structure? Well, the name itself tells this, but sometimes it doesn't say that, but most times it will. Just depends on the fact of how what the formula would be. So the formula would be C4H8. Now keep in mind that if you were to have a structure that doesn't have a ring, the formula is going to be a little bit different. So typically it's CnHn plus 2. So the N just represents how many carbons there are. So if you have 4 carbons, you have 4, that would be 2N plus 2. So it would be 2 times 4 plus 2, which gives you 10. So that if you were to have just a simple single bonded non-ring structure, you'd have a formula in the Lewis structure that looks like this. 2, 3, 4, 5, 6, 7, 8, 9, 10. Now each of these carbons here are all 4 domains, because there's nothing there that separates them. They're all the same. So this will have a tetrahedral and sp3 hybridized carbon chain. So each of these carbons would have the same hybridization and molecular geometry. So now there's one other example that I want to show you here, and that is if you are dealing with a structure where you have this configuration. Now, so this is where we're taking that carbon chain that we just saw before, and instead we're putting a double bond in between. So now the good thing is that all the carbons are going to be the same. They're symmetrical the whole way around. And so we're just going to focus on one individual carbon atom here. So now in this carbon atom, we're going to see that we have 1, 2, 3 domains. And so that is a trigonal planar geometry, and then it also is sp2 hybridized. So again, all of these will exhibit that same hybridization and geometry. So what we're going to do is I'm going to stop with this video, and what we want to take from this is, when we get into these molecules that have multiple centers, you have to be very careful in how you select. You can't just say that they all are the same, because they can have variations. It really depends on what's bonded and how the electrons are arranged around each center within that molecule. So if you have any questions, you know how to get in touch with me. Thanks. Bye-bye.